Welcome to the last video of Chapter 9, that is if you don't count the study guide. So there's one formula you kind of need to know. It's called percent yield. And that's what it is. So we have two words to define the actual and the theoretical yields. So the theoretical yield is defined as the maximum amount of a given product that can be formed when the limiting reactant is completely consumed. Yeah, you're probably going, right. So what does that actually say? If everything is perfect, this is what you should get. This is what the stoichiometry, all that math crap should say you should get. But we know lab work's not perfect, right? So the book definition of actual yield is the actual amount of a given product as the percentage of the theoretical yield. Yet that doesn't make a lot of sense either. Well, here we go. How about this? This is what you get in the lab. So the theoretical yield is what you should get if your lab skills were rockstar perfect, and nobody's are. The actual yield, well, that's what you really get in the lab. Let's take a look at this. In a lab, a careless chemistry student produced 0.56 grams of silver in a single replacement reaction of copper and silver nitrate. The student should have made 1.73 grams. So, what's her percent yield? Well, you recall this formula, see? It's actual over theoretical. Well, let's get a decent pen color here. Oops, I should probably turn my board on. It's amazing how well it works once you actually turn it on. And I'm so brilliant, not only did I not have it plugged in, I didn't even have it turned on. Okay, here we go. So, this number is what we actually got in the lab. And I'm going to divide that by the theoretical yield. That's what we should have gotten. That's what the stoichiometry said we should have gotten. Times that by 100, whammo, 32%. That's it. We're done with this type of problem. This is an example of a question I would enjoy putting on a test because it's one of those multi-step, multi-part questions. And I'm assuming you've already read through all of this problem. So then we're going to finish it up with a percent yield. Let's take a look at the first part, and that's balanced chemical equation. And I like to write down what I have directly underneath those and what I'm solving for. Now, it's in kilograms. You're welcome to convert to grams, but if you convert it to grams, at the very end, you're just going to have to convert it to kilograms, and it actually works just fine to pretend that says grams. As long as the answer is the same as what you start with, in this case, kilograms to kilograms, you don't need to cancel back and forth and convert. If you don't believe me, go ahead and do it your way. Because it's a limiting reactant problem, I first have to find the number of moles. So go ahead, pause the video, find the number of moles of both hydrogen and carbon monoxide. Which now I'm doing for you to show you. There you go. And now we're doing the next one. So, once you're done with that, who's the limiting reactant? Yeah, you can't tell yet. Remember, you have to do that mole ratio thing. Now I went ahead and chose carbon monoxide because that number is still in my calculator. And now we want to do a mole ratio. So from the balanced equation, I know there's 1 mole of carbon monoxide for every 2 moles of hydrogen. So that's the amount of hydrogen I need. Do I have enough? Well, absolutely I have enough. So that means the carbon monoxide is the limiting reactant. So somewhere on your papers, there's it is, I would write limiting reactant equals carbon monoxide. All right, that's the one we're going to use to find the final answer. Well, at least the amount of product. So we need to do a mole ratio. In this case, it's 1 to 1. And now the molar mass. Phew. Well, actually, if you remember, that's really in kilograms because we started in kilograms. Now, the second part of this problem asked us to, I'll try to say that again. The second part of this problem asked us to determine the percent yield. So if that's how many grams of methane we actually made in the lab, what is the percent yield? Now these, you do have to have these in the exact same unit because you're dividing. So I went ahead and converted these grams to kilograms. Now bring in the formula, the actual over the theoretical. In this case, we're going to take the actual yield, divide it by the theoretical yield, multiply times 100. There's our percent yield. Not too bad, not too shabby. The final part of this question is how much of each reactant is left over? Well, one of them should be really easy. The limiting reactant, yeah, how much of that's left over? None, nada, no more of that is left over. Now, what I can do to solve this problem is go ahead and use the limiting reactant. There's my pen. I'll find my pen today. We're going to use the limiting reactant because however much of that I used, I can figure out how much hydrogen was consumed. So using the moles of carbon monoxide, I'm going to do a mole ratio with the hydrogen. And now I can find out how much hydrogen I actually used to make all that carbon monoxide go away. What do I do with that number? Well, I first need to convert it to kilograms. And if you remember, because we did all of this in terms of kilograms earlier, that is the kilograms. So how much do I find out is left over? Simple subtraction problem. There's 1.09 kilograms of hydrogen left over. And because that problem wasn't confusing enough, I thought I'd hit you with just one more. Now, this problem, I didn't do the whole kilograms to grams thing. I left that alone. Everything's in grams. So once you've decided you've read through this, you're done listening to me talk, pause the video, go through the problem, and see what you can do. Again, I like to write down everything I have, and because there's amounts of both, and I need to find the amount of product, it is a limiting reactant problem. So, convert those both to moles. No, really, go ahead, do it. I'll wait. So who's the limiting reactant? Yeah, if you're going, duh, Norton, we can't tell. One more step. Rock on for you. Okay, here we go. I chose that one. Doesn't matter which one you use. Now we're going to do the mole ratio of the two reactants. So, do we have enough hydrogen? Oh yeah, we have plenty of hydrogen. So we better indicate our limiting reactant, huh? So limiting reactant is that guy. So that's the one I'm going to use to figure out the amount of product. I'm going to do a mole ratio now with the product, then the molar mass. So that's how many grams of ammonia is produced. Well, of course, this is a multi-step problem. The question also wants to know what the percent yield is. So you're going to bring in the formula. That is what was actually produced by the lab, even though the math said we should get that amount. Multiply it times 100, boom, percent yield. The last part of this problem wants to know how much of each reactant is left over. Start with your limiting reactant. Well, that's easy. There isn't any of that left over. Then use that to figure out how much of the hydrogen was used. Because if we use all of the nitrogen, make it go away, how much hydrogen did we have to use to make that happen? So using a mole ratio, and then the molar mass of hydrogen, we end up with that many grams of hydrogen used. So how are we going to figure out how much is left? Well, that's easy. You're just going to subtract it. And we are finished with this problem. Up next, thermodynamics. Of course, that's after the study guide and after the test. And the lab. Yeah, that too.